In this video, we look at electron spin. The electron, like most particles, has an intrinsic angular momentum called spin. Visually, you can think about it with a classical picture. The electron is a negatively charged spherical particle spinning around itself. However, don't push this analogy too far, as it is not entirely correct for a quantum particle. There are two issues. First, there is no well-defined rotation axis in the quantum world. And second, the electron would have to spin faster than the speed of light to be consistent with its spin angular momentum in this picture. Nevertheless, this so-called vector picture of spin is often useful. The spin angular momentum of the electron has one fixed immutable value. Its magnitude is h bar times the square root of s times s plus 1, where s is the quantum number is equal to 1/2, so that the magnitude is equal to h bar times the square root of 3/4. Note that this is a half integer quantum number, the first time we encounter it. This is unlike the orbital angular momentum of the electron in a hydrogenic atom, which can have varying magnitudes, which are h bar times the square root of L times L plus 1, where L can vary and assume values from 0, 1, 2, and so on. When measuring the projection of the spin angular momentum along an axis of choice, let's say the vertical one, you can get only two possible values, plus h bar over 2 or minus h bar over 2, written as ms times h bar, where ms equals either plus 1/2 or minus 1/2. This is very similar to orbital angular momentum, where we have ml, h bar as a projection, with ml running from negative L all the way up to positive L. In both cases, the projection is quantized. Now, what about the number of states? There are a total of 2 possible states for the spin, just as there are 2L plus 1 possible states for the orbital angular momentum. The spin wave functions for the stationary state for ms equals plus 1/2 is just denoted by alpha, or called spin up. For ms equals negative 1/2, it's called beta, or spin down. The wave functions for the orbital angular momentum, of course, are the LMs, the spherical harmonics. In terms of operators, spin is completely analogous to orbital angular momentum. The square magnitude is represented by s square, and when that operates on alpha, you get h bar squared times s plus 1 times alpha. If it operates on beta, we get h bar squared times s plus 1 times beta. For the orbital angular momentum, we have L hat squared operating on YLM equals h bar squared times L plus 1 times YLM. The projection along an axis of choice, which is most often the vertical axis and labeled Z, is represented by the operator SZ. Operating on alpha, it will give plus 1/2 h bar times alpha, and operating on beta, it will give negative 1/2 h bar times beta, in complete analogy to LZ operating on YLM, which gives m sub L times h bar times YLM. As always, the states alpha and beta are normalized and orthogonal. Since there is no spatial variable associated with spin, it's best to write this in the more general bracket notation. Bracket alpha beta equals 0 for the orthogonality, and bracket alpha alpha, which is the same as a bracket beta beta, equals to 1 for normalization. How can we picture these two spin states, alpha and beta? Well, let's draw the spin angular momentum vector. We know its length. It's h bar times the square root of 3/4. So if we start at the origin, we can draw a sphere of radius of that particular radius, which is about 0.866 h bar. Next, if we measure the projection along, say, the vertical axis, we can get either plus 1/2 h bar, or we can get negative 1/2 h bar. So the tip of the vector will be found somewhere on this horizontal circle on the sphere. Or, if the quantum number is minus 1/2, it will be on this circle. Or in other words, the vector is going to be somewhere on this cone, either in the upper cone for m sub s equals plus 1/2, or on the lower cone for m sub s equals negative 1/2. In the vector model picture, the direction of the angular momentum vector represents the rotation axis of the electron. So these two cones tell us two things about the rotation axis. First, they indicate that the direction of the rotation axis is not completely known. Its position on the cone is not knowable. Its orientation is delocalized on the cone, just like the position of an electron in space in an orbital is delocalized. Second, the cones indicate that the rotation axis is never parallel to the z-axis. When we say spin up, the spin is not actually pointing straight up, but is on the upper cone, which is off from the z-axis. In addition to the two stationary states alpha and beta, we can form superposition states. For example, alpha plus beta over square root of 2. So it's not entirely correct to say that an electron spin can only be up or down. Rather, it's better to say that if you measure the spin angular momentum along the vertical axis, you'll find the electron spin either up or down. For the alpha state, you always find up, and for the beta state, you'll always find down. For this superposition state, you'll get up in 50% of measurements and down in the other 50%. We can now include the electron spin in the overall wave function of the electron in a hydrogenic atom. It depends on 4 quantum numbers total. So psi of n, l, m sub l, m sub s. The wave function is a product of a spatial part, psi n, l, m, l, times a spin part, alpha for spin up, or psi n, l, m, l, times beta for spin down. In summary, first, we have seen that the electron has an intrinsic angular momentum called spin. Second, we can approximately picture this by the electron spinning around its axis. Third, there are two spin states which are stationary, described by the quantum number ms, which are called alpha and beta, spin up or spin down. And last, the overall wave function of the electron in a hydrogenic atom is a product of a spatial wave function and a spin wave function.